Good morning. It is Thursday, March the 17th, 18th, March the 18th.
Just the 18th, yes.
Okay. All right. So the first thing we're going to be able to do is I started the video a little late here. We're going to be able to make sure we can identify each substance according to the three definitions of acids and bases. Okay. So this is a Bronsted-Lowry base because it's accepting the hydrogen from the water. It is a Arrhenius base because it's producing the hydroxide. It's a Lewis base because it's donating the pair of electrons, that lone pair on the nitrogen. So to write the Kb expression, it's super easy. We're just going to go products over reactants. C6H5 NH3 plus times OH minus all over C6H5 NH2. That should be an easy point. Now, sample of aniline is dissolved in water to produce 30 milliliters of a 0.1 molar solution. The pH of the solution is 8.82. Calculate Kb. Well, if I'm going to calculate Kb, that means that I have to know all three of these things. Okay? So, how do I know my OH minus? From the pH, right? So I know if the pH is 8.82, what's my pOH going to be? 5.18. So pOH equals 5.18. Therefore, OH minus, how do I calculate it? 10 to the negative 5.18. And so the OH is equal to 6.6 times 10 to the negative 6. I should have known that. Okay? So, and for every one of these, we get one of those. So these two are always going to be equal. So it's going to equal that 6.6 times 10 to the minus 6 squared divided by this 0.1 minus 10 to the minus 6, which we can pretty much say is still 0.1, right? Because, I mean, you can actually plug it in and say 0.1 minus this, but you're going to find that 3 or 4 sig figs, it's still 0.1. But I always would say go ahead and put it in there. So doing all of that, that equals times 10 to the minus 10. 4.37, is that what you said? 36, so I'm going to say for just 4.4. Although we probably, on the OH, I think we can probably go one more decimal place, but this isn't going to be a sig fig problem, so that's not an issue. All right, so the solution prepared in part B is titrated with 0.1 molar HCl. What's the significance of 0.1 molar HCl? This is what you go back and you look at. It's the exact same concentration as my base. So how many milliliters of HCl would it take to completely neutralize the aniline? 30. So where are we at 15? That's the half equivalence point. And there's, on that study guide, there's one place I say midpoint. Okay, down at the bottom again, calculate the pH at the midpoint. The midpoint is the same as the half equivalence point. So if you want to write that in on that study guide, I use the word midpoint, but that's the same as half equivalence point. That's again down at the very bottom, like third or fourth sentence from the bottom. Midpoint and half equivalence point are the same, just the terminology doesn't mess you up. So what does that mean at the half equivalence point or at the midpoint? pOH equals Pkb. Okay, calculate the pH. Okay, So I can say then that negative log, the POH, equals the negative log of 6.6 times 10 to the minus 6, which is going to equal 9 point what? 9.36. So the pH is equal to 4.64. Do what?
I got that same answer, but I probably have spent like 30 minutes.
Okay, but that's the trick. I mean, and if you go through and solve and put, figure out how much is reacting and plug all in that in there, you're just going to find that these two are going to be the same. They're going to cancel each other out. It's going to be plus the x and minus the x. But knowing that at the half equivalence point, so always check for that, because that's a common thing. Now, why is the pH at the half equivalence, and why is it going down?
Adding acid.
Okay, so I'm adding acid, okay? So it drops quickly, and then, okay, it starts to go level. Yes, sir.
Why wouldn't you do the negative log of 4.4 times 10 to the negative 10?
You know what? We should have. And I was trying to justify why it was so low, because it really shouldn't be quite that low. All right. I made a careless mistake. I went fast. This is not KV. This is KV. All the right concept, I just plugged in the wrong number. So,
You have the right answer, you just put the wrong number.
well, somebody told me the right answer then. 4.4 times 10 to the minus 10. That's what comes out to 9.36, and then 4.64, okay? Because this is KB. Thank you for showing that. Equilibrium expression. We should all know how to be able to do that. We've been doing that for a month and a half now, okay? Calculating KB. Just always remember, when you're given the pH, you're given the H plus and the OH minus. So you automatically know what these are. If I'm going to find KB, I have to know what all three of these are. It tells me my initial, this is X, 1 minus, or initial concentration minus X. Okay, or always. All right? Anybody have any questions on those? Now D is the fun one. So there's multiple steps. Now at the equivalence point, what's the only thing that's left in the solution? The salt. And so we're only interested in the conjugate acid part of the salt. We're not worried about the Cl minus because it's a spectator. So the reaction at the equivalence point is CH3, NH3 plus. And what type of salt is this? Acidic or basic or neutral? So what ion is going to get produced? H plus, okay, not OH minus. So we're going to get CH3, NH2 plus H plus. Now, okay, so this is the secondary reaction. The first reaction is completely done. We've added exact number of moles of acid, moles of base. There's no more reactants left. We only have the salt in the water. Okay, and if you wanted, you could put plus H2O and make that H3O plus. Either way would be 100% correct. Now, in order for me to calculate the pH, I have to know, in this case, the Ka. So the Ka of CH3 NH3 plus, how do I find that?
1.9 times 10 to the minus 14 divided by 3.
And it was 4.4 times 10 to the minus 10. So the Ka is going to equal 2.29 2.29 times 10 to the negative 5. Okay, so there's Ka. I need to find H plus, that's my ultimate, which means I need to know my initial concentration because I know my change is going to be minus X, and plus X. Okay, we're assuming 0 and 0 here. So how do I find this concentration? This is the tricky part, or it's what? How do I find this? Okay, you are very, I think you're saying it right. Where did all of this come from? From the methylamine that you originally put in there, right? So however many moles of an aniline you put in, that's how many moles of this that are going to get produced, divided by now the total volume. Okay? So the concentration of the CH3 NH3 plus is equal to the initial concentration of the aniline, which is how much? 0.1. How many milliliters did we have?
30.
Which is, and we can keep it at 30 milliliters because we're going to end up dividing by milliliters as well. What now, at the equivalence point, how many milliliters is there now? 60. So this makes the math easy because it's just going to be half. So it's 0.050 molar. Now I have my initial concentration of 0.050 molar. Now it's a weak acid problem. Okay? So I can go to my shortcut now. I can say H plus is equal to what?
Square root of 2.29 times 6 and
0.05 times Ka. Which equals so then pH is equal to the negative log 1.07 times 10 to the minus 3 is equal to
2.97.
now this year this kind of threw a lot of people off because the pH was so low at the equivalence point. But you're starting with a very weak base. Okay, so
I was gonna ask, why, since it's a weak base and strong acid, why would it be at the equivalence point when there's equal amounts?
because the salt that's produced, we have equal amounts of acid added and base added, but it's not making a neutral salt. It's producing a salt that does a secondary reaction with the water. Okay? Now, if that's why with strong and strong, you get a neutral salt, so then the ions just float around and we get the pH at 7, which we expect. But when you have a weak with a strong, you either get an acidic salt or a basic salt that does a second reaction and goes back and produces more H plus or OH minus. That's why we have to look at a completely new equilibrium at the equivalence point, because we're no longer dealing with the same one that we were dealing with all the way up to that point. So which indicator would be the best? Okay, this one right here. Because the pKa is closest to the pH at the equivalence point. Now, here's the good news. You totally screwed this up. You get the pH to be 8.92. Okay? Well, let's not do 8.9, it's too close. Let's go 8.1. Well, which one would you pick then? Litmus. And you get your point for this, even though this one's completely wrong. Because based upon your wrong answer, you chose the right one. Okay? Yes, ma'am.
So the part B, like on the example problem we did in class, you calculated the concentration of the salt by saying like moles of acid added.
Okay, it's going to be the exact same thing. Because at the equivalence point, moles of acid equals moles of base. So you can pick either one. I just picked the one, the given information. Since that was given, I'm just gonna use it, but you could have used the acid in this one. Because we know we added 30 milliliters and it told you that the acid was 0.1 from the graph or from your later calculations, you knew it was 30 milliliters, so you could have used that one too, but it would have been 0.1 times 30, the exact same thing. That's the hardest part, because there's so many steps. None of the steps individually are new or hard. It's just remembering the order, remembering to do them all. Questions, questions, questions. All right, so if I have a buffer at my half equivalence point, okay? At the half equivalence point, I have equal amounts of this and this. So with a 50-50 buffer, what's the reaction when 0.01 mole of HCl is added? What's the balanced equation?
That'd be hydroxide.
No, if you're adding acid, what are we adding?
But like in the original.
Oh, I did it backwards, yeah. I guess I got water. I was really kind of going that way. Obviously, you guys got to keep me straight today. Okay? So if I have this reaction, I add acid, what's it going to do? That's kind of the way I look at it, but to write a balanced equation, which way is the equilibrium going to shift? To the right, okay? So, is this the acid or the base? So that makes this the conjugate acid. Which one is the acid going to react with? The base, right? Acids react with bases, not with another acid. So it's going to be CH3NH2 plus H plus, we don't need it, and that's going to go to CH3NH3 plus. So then B, what's the reaction when 0.010 mole of NaOH is that? So we need to be able to know that when you have a buffer, if you add acid, it reacts with the base. If you add base, it reacts with the acid. And just write the equations one way or the other.
Why wouldn't the H plus from the HCl react with the OH minus?
It does. I mean, you can look at it either way, but to write the equation, you're just going to say that the H plus is being added here. Okay? Well, actually, you could say, I think in terms of Le Chatelier's principle, it's easier to see it here, and then the reaction shifts this way to replace it. But how is it going to shift this way? By this accepting a hydrogen. Right? So really the strong acid's forcing the hydrogen onto this and going. I really think if we were to go to a microscope and see what's happening on the atomic level, I think the H plus probably really is reacting with this. But to write the equation, it's always going to be the base plus the acid, or the acid plus the base. Just to know which way the equilibrium is going to shift, we can kind of think of it like this. But to write an equation, we have to be able to know it's always going to be the acid or the base plus the opposite. Y'all, just remember, once you get through tomorrow, you have a week off. 9 days. Sleeping, back to sleep until the crack of noon. Now, homework for me. I'm pretty sure English is going to make you read books, and
That's
math will
actually
probably give you 50 problems a day to do, but no homework for me. Huh?
Mr. Barrett's making the book optional.
So, are we gonna read it? I don't know. It's an optional book.
Why don't you read an optional book?
Put it for bonus, but I just don't care.
It's for love class?
Yeah,
Where you have like a quiz on it?
no. You have to journal the book, so honestly,
How do you know they read it?
Google quotes and just write it.
Exactly.
I'm not doing it, guys, for the video.
Okay.
I'm doing that.
We have it. The whole world knows now how it's going to work. All right. H2CO3 goes to HCO3 minus plus H plus. HCO3 minus goes to CO3 2 minus plus H plus. Ka1 4.3 times 10 it's carbonic acid. There it is, 4.3 times 10 to the minus 7. And the Ka2 5.6 times 10 to the minus 11. All right. If I want to make a buffer, what should be added together to make a buffer with pH equal to 11? How do we know what acid to pick to make a buffer? Now that's how we, that's what we use to determine the overall pH of a solution. If I put this just into water, 0.1 molar of this, the way I'd get my pH is just by doing this weak acid one here and completely ignoring this one. But a buffer is not just going to be putting one thing in, it's going to be putting weak acid, salt of the weak acid, or a weak base, and the salt of the weak base. We want to find the pKa closest to the pH of the buffer you want. Which one is that? this second one. Okay? So therefore, this is, the pKa is going to be closest because of the 10 to the minus 11th, the negative log of that is going to be close to 11. Okay? So what do I add? Oh, I got to be a little bit more specific, you know.
The same old, basically the same order.
Of what?
What do you want to use?
Well, that's what I'm asking y'all. Given this, okay, what do I mix together? What's a buffer?
Basic acid.
No, no.
Salt plus,
But these are acids, right? So it's a weak acid and the salt of the weak acid. And which one did we say, which equilibrium should we use? So I'm going to add some NaHCO3 and some Na2CO3. Now, it's really HCO3 minus and CO3 2 minus. But you can't ever just go to the store and buy HCO3 minus. Positive and negative are always going to be together.
Why did you pick like NA, like how did you pick that?
NA, or you could use K, you could use any alkali metal, sodium is just the most common. Good question though. And really, if it was like in a multiple choice, you just look for the ratio of the HCO3 to the CO3 2 minus. Okay? So if I wanted to make something with a buffer with a pH around 7, what would I mix? H2CO3, we don't have to add it in, this is already neutral. H2CO3, some carbonic acid, and some sodium bicarbonate. Equal amounts get you the 50-50 buffer. Now, we could use the Henderson-Hasselbalch equation if we wanted to figure out what the exact ratio we needed to add. Okay? But you probably won't have to do that. What else is giving y'all some confusion? Well, we already kind of talked about titration, but I mean, what else about the titration? At any point? Well, again, that's the bonus one you get to look up. Yes, sir.
What's the difference between the equivalence point and the half equivalence point? 1 half.
Thanks, Glenn.
I mean, am I wrong?
Okay. So this is pH. This is always the equivalence point, the middle of the vertical part. That's when moles of acid equal moles of base. Not necessarily a pH of 7. It's just we've added equal moles of each one. The stoichiometry says, okay, all the acids reacted with all the base. So here at 10 milliliters, we're halfway there. We're just half the equivalence. Now what happens at this point, if it's a weak acid, if this is HA, and we're adding NaOH, now we have a 50-50 buffer of HA to A minus. So we say pH equals pKa. So we had the problem, and remember here, at this point, it's almost all HA because it's a weak acid, so most of it's not ionizing, so it's almost all HA. Now you start adding the base starts pulling hydrogens off, making water, so as soon as you put the OH in, it's consumed by the H pluses, making water, but we're producing more and more A minus. But all the way from here to here, we still have more HA than we do A minus. So at this point, HA is greater than A minus, right? Here they're equal, so then from this point to that point, what's going to be true? HA is, A minus is greater than or HA is less than, right? And then what's the only thing present at this point? A minus. Okay, now remember, there's going to be some sodium or potassium or some positive spectator ion with it. Okay? In this case, it'd be a sodium because we're adding NaOH. And then, what's present up here?
OH, Na.
So it's going to be OH minus, Na plus, and A minus, but this is the one that's in the largest concentration. Because the A minus doesn't go away here and the base doesn't react with it. But you're adding a whole bunch of OH minus. Does that answer your question?
Yes, sir, thank you.
Why wouldn't the Na plus be in largest since it's not being used at all? Or is it just not really cared about?
Yeah, we don't care about that. They'll ask about OH minus or A minus.
Okay.
But that's actually probably the right answer.
When you said that it's moles of acid equals moles of H, is it like specifically moles of OH minus and H plus?
Yes, but I hesitate to say that because the secondary reaction then changes that to where then if it's an acidic salt, you're gonna have more H plus, and if it's a basic salt, you're gonna have more OH minus. But from the HA plus NaOH part, yes, you're adding the exact same number of moles of H plus and OH minus. It's just that the NaA is going to react with the water. So I tend to say moles of acid equals moles of base. But that's where we have to remember if it's diprotic or dibasic, we have to put the 2 into that MAVA equals MBVB. That would be more of a multiple choice type question, just FYI.
This might be random, but why can't we say that pH equals pKa at that point?
At which point?
At the half equivalent.
Why can we say that?
Yeah.
Oh, because if I'm saying Ka is equal to H plus times A minus all over HA. Well, if we're saying that a 50-50 buffer, HA and A minus are the same, they're equal, that means these are going to cancel out. So Ka is going to equal H plus. Take the negative log of both sides, negative log of Ka is equal to the negative log H plus, pKa equals pH. Yes, sir.
This is kind of different, but if the titration, like we did in there, if it was like a strong acid and strong base, then you could just use MAVA equals MAVA.
Yeah, you don't have it, the pH is 7 at the equivalence point, there's no reaction, there's no math.
Okay.
Now to find the pH at past the equivalence point, you do the same thing, milliliters of excess OH added divided by, times the initial molarity divided by the total volume, like we did yesterday. Yes, ma'am.
For part D, why do you start with the CH3 and H3 and not with?
Because that's the salt. Because with the aniline, we had CH3, NH2, okay? And we were adding base to that. And it was going to, do I need to add the base? No, because we're adding that, or we're adding, pardon me, we're adding acid to it. And we're making CH3, NH3 plus some Cl minus. Okay, so I'm adding HCl, I'm adding acid to it. So the whole point is that when I do HA, well actually, I'm doing that wrong. Plus H plus here. When I'm looking at HA, I'm getting there, y'all. When I'm looking at the base, this CH3, I don't even need to rewrite it. Once I add the same amount of acid as I have base, there's none of this left. At the equivalence point, all of the reactants have reacted. You don't have to go there. All the reactants, these two things reacted. The only thing I have left is that, the salt. So at the equivalence point, you only have the salt. It's the salt then that does a second equilibrium, a second reaction with the water and goes back to this producing some H+. That's why it's called an acidic salt. So that's what makes that equivalence point more challenging, because you have a whole new equilibrium. You have the equilibrium of the conjugate now, not the acid itself or the base itself. I started off rough, but did I get there to answer the question?
Can you explain the half equivalence point the same way you just explained that, like with the equation and all?
Okay, now well, at the half equivalence point, so let's just say I add 10 milliliters of 0.1 molar acid, and I have 20 milliliters of 0.10 base. This basically is the limiting reactant. So as I keep adding acid, it's making this, okay? But this is getting used up, so there's none of that left. But it's forcing this, so this, however much of this I add, this is decreasing by that amount. This is increasing by that amount. So if I react just enough to react with half of this, that means I have half as much as I used to, and I have half as much more now of that. So I'm going to end up having equal concentrations of each one. So they basically cancel out of the equilibrium expression. You're just letting it saturate, permeate your soul. You know, after you cook a steak on the grill, you gotta let it rest for about 5 minutes afterwards, just to let everything just kind of settle in. Okay? What else? Okay, let's label these as acidic, basic, or neutral. These are all what? Salts. Is that going to be acidic, basic, or neutral? How do I know? Strong base, KOH, strong acid, H2SO4. Neutral. What about sodium chloride? Strong base, weak acid, right? Therefore, it's basic. Now, why is it basic? What's the equation? When I put that into water, what's going to happen? ClO2 minus plus water. And if it's a basic salt, what's it going to produce? OH minus. So we're going to get HClO2 plus OH minus. What about this one? It's acidic. So which part is going to react with the water? NH4 plus. Now again, well, I'll go ahead and include water on this one. So what will it make? Plus what? H3O plus. So we need to be able to identify salts, acidic, basic, or neutral, and be able to write an equation for how they're going to react with water, why they're acidic, basic, or neutral. And what about this last one? It's neutral. We all good with that? That's a for sure. I'm kind of giving you all kinds of hints, what you need to study.
What kinds of buffer problems do you have to deal with? Just like,
Well, this really technically is not a buffer problem. First off, let's talk about identifying a buffer. The biggest thing is just calculating the pH of a mixture of a salt, weak acid, and salt weak acid or weak base, which you just use your Kp expression, but we'll do one in a second. But which ones of these would make a buffer? An effective buffer. What is this right here? Strong acid. Does strong ever make a buffer? No. Okay? No. Strong base? No. But here is the base, and then the conjugate, the salt of that base. So this would be your buffer. Would the pH of this buffer be above or below 7? Because it's a base with its salt. So whatever if it's an acid with the salt of the acid, it's going to be an acidic salt, an acidic buffer. If it's a base with the salt of the base, it's going to be a basic buffer. Now, one mistake that students have made in the past is when a multiple choice question are asked, which is, which would have the higher pH. They sometimes think in their minds higher pH is stronger acid, because you just think higher concentration of the acid makes it stronger. But pH, remember, goes the opposite direction. 0 is the strongest acid. Okay, so just make sure when you're reading about pH, strong, get your brain going in the reverse direction. Okay, a second way to make a buffer. The first way is just a mix. The second way we can make a buffer, and then AP likes to ask these questions, is that you take a weak acid, such as any weak acid, HA, and you combine it with a strong base, but you only go part way. You don't go to the equivalence point. So again, if I have 20 milliliters of 0.1, and I add in 10 milliliters of 0.1, is there any of this left? But I've made A minus. So I've created the buffer. So a partial neutralization, you can make a buffer with a weak acid and a strong base, or a weak base and a strong acid if you have a partial neutralization. You only go part way, you don't make it all the way to the equivalence point. Most of the time they ask about the half equivalence point, the 50-50 buffer. But anywhere along that line, which is why the pH stays relatively constant in our graph, it's horizontal right there, because we're creating a buffer. Now, there's always a little uptick because at the very beginning you don't have a buffer, so you're adding a bunch of OH minus, so it goes up, and then the buffer makes, and then, when you exceed the capacity. But that's another thing, buffer capacity. If I have 0.1 molar and 0.1 molar versus 1 molar and 1 molar. Remember, it's 50-50, so these cancel out. So pH equals pKa regardless, but what's different? Okay?
It's less resistant. There's more of it.
Less resistant, okay, keep going. As I'm adding, which one can handle me adding more acid or more base? The 1 molar, because it's going to take a whole lot more before it runs out. So it's what we call the buffer capacity. The more concentrated the buffer, the greater capacity. In other words, the more acid or base it can handle before the pH begins to change significantly. Doesn't change the pH of the buffer because the ratio is still the same. It just, because 0.1 over 0.1 is the same as 1 over 1. So remember, Ka is equal to H plus times A minus all over HA. So if these two are equal, they cancel out. So H plus is going to equal Ka. If this is 0.1 and 0.1, or 1 and 1, or 10 and 10, this is going to cancel out regardless. But you can just have a greater buffer capacity. You can handle more acid or base before it, pH begins to change significantly. All right. What type of buffer problems do you have to do? Let's just say 1 liter, make the math easier. All right, so somebody go to page 1104 in your book and find lactic acid Ka for me. And what's the formula of lactic acid? Is it not in there? CHOH, COOH?
Or H C3H5O3.
H5O3. We'll go with that.
There's another acid on the up here.
There's another what?
It's HC3.
Oh yeah, so there's your acid, okay. So that makes sodium lactate NaC3H5O3. Okay? So my Ka of lactic acid
1.4 times 10 to the negative 4.
So again, I don't like writing all that, so I'm just going to say HA is going to go to H plus A minus. This is my A. This is my A minus. So I have HA. I'll just call that HA like that. And A minus. I have an acid and I have the salt of that acid. So my initial concentration of HA is going to be what? 0.5 divided by 1, so 0.5 molar. But what's my initial concentration now of A minus? 0.4. So this is a common ion problem. So now rather than it being 0 and 0, now I have some of not only of my acid, but I have some of the salt added in from a second source, from the sodium lactate. Okay, so I have a common ion. So what's my change going to be? Which way does this still have to go? To the right, because it's 0. So it's going to be minus x plus x plus x. So I'm going to say then that 1.4, 10 to the minus 4th, is equal to x times 0.4 plus x all over 0.5 minus x. But what do we get to do? X is negligible. Okay, because we're at 10 to the minus 1, 10 to the minus 4, so we're 1,000. And so x is negligible. So therefore it's going to be 1.4 times 10 to the minus 4th times 0.5 divided by 0.4 is equal to H plus.
Uh, 1.75 times 10 to the negative 4.
So then pH is equal to the negative log of that. Notice we're close to a 50-50 buffer. 10 to the minus 4, we're pretty close to 4 on the pH. So we make a buffer, the pH of the buffer is going to be close to the pKa of the acid that we're using to make the buffer. So really, buffers are one of the more difficult concepts mentally, but the math is one of the easier problems. It's just a common ion problem. The one we did, these problems here are just a straight equilibrium problem. X, X, initial concentration minus X, so they're just like we did. See, we're ready. You got this. Piece of cake upside down, no problem. You asked good questions though today. Went through all of that one. So this is that other packet, since we have a few minutes. I don't know, did we do any of this one? Seems like I remember making a comment about soft drinks. Could have been in the other class.
Yeah, I think we did it.
We did?
Yeah, we did.
Potassium sorbate, commonly added diet soft drinks and preservative. A stock solution of known concentration must be prepared. A student titrates 45 milliliters of the stock solution with HCl. Okay? So what's being put into, write the net ionic equation of this and this. So where are my spectators going to be in these two? Cl and the K, right? So my net ionic equation, you don't have to do the total to get to the net. I mean, they just want the net. So if you can do it in your head like we're doing. So it's going to be C6, H7, O2 minus, plus H plus, and what's it going to go to? You just put the H out front. So how do I find B? I'm given a volume. What is this? The volume of what?
Acid.
So that's VA, right? What is this? MA, molarity of the acid. A stock solution, I have 45 milliliters of the stock solution, so what is that? Volume of the base. And what's the question asking? Calculate this. What is this? This is the molarity of the base, right? That's my unknown. So again, we're doing a titration. They give you the volume and the molarity. That's your clue. It's going to be MAVA equals MBVB. So MB is equal to MAVA over VB is equal to 1.25, 29.95 divided by 45.
Does that equation only work if you go for one?
Say it again?
Does that equation only work if you go for one?
Yes. So if the pH at the equivalence point is 2.54, which one of these do I want to pick? .54, I want to get the one that's closest to 2.54, so I'm going to use the thymal blue. That's an easy money point, no math. You just need to know that the pKa of the indicator needs to be as close to the pH as possible at the equivalence point. Because that means that's when it's going to change colors. And then calculate the pH at the half equivalence point. Okay? The pH at the half equivalence point, how do we do that? pH equals pKa. All right? But this is KB though, right?
No,
It gives you K in your top.
It gives you Ka. It should, I think it'll work either way. If we did POH equals PKB and then subtracted. Okay? So pH equals pKa, so we can just say that that's what the pH is, going to be, take the negative log of Ka. What's that equal?
4.77.
Okay, so at the half equivalence point, so we're adding in HCl, so we know we're making an acidic salt, okay? So being below 7 is logical. The initial pH and the equivalence point are plotted on the graph. So what's the titration curve? What did we just say the pH at the equivalence point was?
2.5.
Now that, oh yeah, what did we, I mean, at the half equivalence point? 4.74, so if it took 29.95, so basically 30 milliliters, where's the half equivalence point? 15. And what did we say the 4.77, so we're gonna be somewhere right here. Is your half equivalence point. So we're gonna come down. Oh, pardon me, is that wrong? This is the half equivalence point, not the equivalence point. It's gonna look something like that. Just find where your half equivalence point is, put the pH. You know you're gonna come down, it's gonna go kind of level through that half equivalence point. It's gonna go vertical at the equivalence, and then it's gonna go back level. So then F, the pH of the soft drink is 3.37, okay, after it's been added. So 3.37 is where on our titration curve? If this is point A, point B, point C, point D,
Between B and C.
it's between B and C, right? It's somewhere over here. So which one is going to be in, well, actually it's down here. Which one's going to be in greater concentration? Well, again, look, what's our equilibrium? We're doing C6H7O2. Go back to your original equation. Okay, and that was going to our initial equation was what? I can't remember, what was it reacting with? Did we say with plus acid? But plus H plus is going to HC6H7O2. So are we past the 50-50? So which one are we going to have more of? This one. This is the reaction that's taking place when you put this into the water. It's going to make this, okay? So if you're past the 50-50 point, you have more of this than you do of that. So you're not doing the, don't go back to the acids, go back to your original equation. This would have been one of your 10-point long questions. You have 3 10-point questions that are, quote, long. And then you have 4 short questions that are 4 points each. That adds up to 46 points. Then they do a scale, 50 over 46 times whatever, however many points you got out of those 46. Make it out of 50. All right, now I just want to talk about this one. This was a short question. Just 2 parts. So how would we do A? Think about A. I'm not going to say how to do it. How would we do A?
Find the concentration of OH minus.
Why OH minus?
Of the H3.
So
Look at the equation above it.
And then ice table.
H plus equals square root 0.75 times 1.12 times 10 to the minus 10. Okay, it's just a weak acid. Yeah, it tells you that it's an acid, it gives you the equation, gives you this initial concentration of 0.75, 0 and 0, minus x, plus x, plus x. Now this is the good one. It says for a certain reaction involving phenol to proceed at a significant rate, the phenol must be primarily in its deprotonated form. The C6H5O needs to be in this one. In order to ensure that that is deprotonated, the reaction must be conducted in a buffered solution. On the number scale below, circle each pH for which more than 50% of the phenol molecules are in the deprotonated form. When does it go more over 50% of this than that? Past the half equivalence point. What's the pH going to be at the half equivalence point? Pka, right? Which is 10 to the minus 10. So we need to be past 10. Well, actually, it probably comes out to 9 point something here. So we can say 10, all of these. Because anything over that is going to push it to the right. Because the OH minus, as you keep it, you get more and more OH minus here, that's going to keep pushing this to the right. It's going to pull this H plus off, or if you think about it as reacting with this, making water, pushing it to the right. So again, we're over the 50. This is a different way of asking, where are we at the half equivalence point? Can you see how many different ways and questions they've asked about that concept? pH equals pKa at the half equivalence point. How do we find that half equivalence point? Okay? So that's a big one to understand. All right, you got lots of practice problems. You have your Princeton review that we haven't even looked at that you can go through, and it gives a synopsis, and you can look at some practice problems in there. Y'all, I'm keeping on. We're pretty good. I wish we had time to have done the lab, acid-base neutralization lab. That's the only thing we're really lacking. Probably have been good to be able to spend a day doing Princeton review, but we don't have that luxury, so study hard, do your best. You'll have all the spring break off. I get to use spring break to grade your test. And